So please, sir.
Thank you, Sajid. And thank you very much indeed for a very good introduction. I am obliged. And I thank the organizers for giving me this opportunity to interact with you all. So the topic assigned today to me is an introduction to multivariate analysis. But as in, I was looking through the course schedule, we have already touched upon the basics or what does it mean. So let us proceed and we see what is a multivariate analysis. So it's a very vast topic actually, and it comprises of so many things. Though it has a application in statistical science, biological science, and since I'm being a breeder, we focus it on animal breeding aspect. And we use often these techniques for in our animal science data. So multiple regression analysis is one of the very good technique and widely used techniques where we used for the prediction of a variable, an outcome variable based on certain independent variables. We use discrimination analysis to discriminate between one or two populations. We can use genetic divergence analysis where we can see whether the two individuals are from the same or from the different backgrounds, genetic backgrounds. We do canonical variate analysis where we can see how we can classify into one or the other groups, and then we can do for the principal component analysis. So these are basically nowadays being used with the help of artificial intelligence or machine learning. That is the recent advances. But since these are the conceptual lectures, so we will go towards the concepts and we will see as if we are doing it with the hand, and later on it can be done with the help of computers. So coming to that, when we say these multivariate analysis, particularly this discriminate analysis or component analysis or regression, so one should be very much clear that where we are going to use. We are going to use regression for prediction, discrimination, and studying the genetic divergence. That means we are going for the classificatory problems, and these classificatory problems are called as supervised problems in artificial intelligence. And if we go for the dimensional reduction like principal component analysis, these are the unsupervised methods of estimation. So starting from the very basic, this is a scatter plot, and everybody can predict what is the correlation between two variables. So we'll start with two and we'll go to the multi, right? So you can see if there is no correlation, then how does it appears? This is no correlation. And this is the plot. If the correlation is negative, that means with the increase in x, the y is decreasing. So this is the direction. Okay. And if we go with the perfect positive correlation, that means with x and y are more than 90 or 100% correlated, this will be the situation. And likewise, you can think of. In correlation, there are two variables and each of them are treated at par with each other. While in regression, when we say linear regression, we classify, we account one variable as a predictor and other as an outcome. Another way of saying is predictors are independent variables and outcome depends upon these predictors. So when we predict an outcome using some independent predictors, that is a technique, we call it as a linear regression. If it involves single trait, it is simple linear regression. If it is requires multiple traits in the model, it is called as multiple linear regression. But the purpose is same. So let us start with this equation. That equation is y equals mx plus b. Everybody knows that in class 6th and 7th, we were being taught that this is represents y represents the straight line. So let us see if there are two variables, say x and y is perpendicular on x, and there is a equation given by y equal, this blue line is given by y equal mx plus b. So what is b? So b is the intercept where for the value of x, the y is being sought out. Here in case, the positive value of x here is having a negative value of y. So this is the intercept till this point. Okay. So that is what we mean when we say mx plus b, and m is the slope. That means how the x and y are related, at what rate they are related, positive or negative. Here it is positive. So it is this slope, and we call it this angle as a theta. And we say that this is m, that is delta y, this is delta y by delta x. That is from one position x1 to change in x2, then one position in y1 to change in y2. So if we divide these things, we will get this slope, that is delta x by delta y by delta x. So what does that slope can be defined as? What is it? It is a slope that, suppose for 2 means that every 1 unit change in x yields 2 unit change in y. If it is 2, slope is 2, that means that every 1 unit change in x will change 2 units of y. This is slope. And prediction, if you know something about x, this knowledge helps you to predict something about y. And this concept, though sound familiar with the conditional probabilities, but it is different. How? In conditional probability, if the event B occurs, then what will be the probability of occurring an event A? So when B has happened, it influenced the probability A, which is not same as when we have actual probabilities of A and B, right? They will be different. So there is a condition that B occurs first, then A will modify accordingly. But here, for each value of y, it is a prediction. That is a probability, and this is a prediction that for each value of y, you can quantify how much change will occur in for each quantity of x, how much change will occur in y. So the regression equation says that for a given x, the I value of x, any value of x, the expected value of y equals the population mean denoted by alpha plus regression coefficient beta and the x value itself. This is the case with the simple linear regression. And if we want to predict a value for an individual, so the predicted values are generally denoted by y cap. And if we see, this is the fixed effect or the simple linear regression, or this is the effect which comes on that line which we fit into the data set. We will see that later also. So this is fixed and it comes on the line, whereas the data points may not be the same and it will differ, and how much amount they will differ, it is called as a normal distribution or random error. Why we say random? Because you cannot fix it. You cannot predict this. But another way of looking at this prediction model is that it has something that you have taken one effect in prediction, that is x1, in prediction of y1, right? So you have taken only one effect, but there could be more than one effects which are governing the y. So it is not exactly the entire variation is being explained by this particular trait x1, but y1 also contributed by some other factors. But what are those other factors? We have not taken into account. So we call it as error or residuals. Whatever has been remaining, we call them residual. It is not the error in the measurement. It is the variation which is not being explained through this model. because we have taken into account the regression of only X, but other factors which might have been contributed to the variability of the Y or the outcome variable, we have not taken into account. So if we say what is a standard error, so standard error of Y given in X is the average of all the variability around that regression line. So we have always taken X here. You can see this is X and this is Y. So if we say Y on X and this regression is the observed values, or what we have actually got it as a result of regression of X, that is Y is an outcome, and based on the values of X what we got. So the error, standard error, it contributes each individual data point and the distance from the regression line. So you see they are in the same line, and the average of all these values, how much they are differing at this particular point on the regression line, is called as the standard error. Whereas variation is that if some data point is lying here, some is lying here, some is lying here. So this is the variation of X on Y. This is the actual variation of this data point, and this is the actual variation of this data point. That is the distance or the scatter from that point. So it could be different, but standard error is the average variability around the regression line. This is an important concept and an important regression picture. If we understand this, we will be able to understand how the regression works. So let us see, there are two variables, X and Y. X is a independent predictor, Y is an outcome. Suppose the average of Y is this is the naive mean, simple mean of Y. Whatever data points we have for Y, it is this value denoted by this dotted line. And this solid line is the Y cap, or the predicted line, which we have done for the estimation of regression. So this is the simple linear regression, and we say that it is having a slope of beta with X and plus alpha and intercept. So this is a Y cap. This line is a regression line, is a Y cap. And these are the individual values which is far away from the regression line. So let us assume that yi in any value, which is how much it is differing. So we say how much it is deviating, the square of deviation. That means we will not take into the sign. So to overcome the positive or negative sign, we will take all the positive signs. So it is the A is the total variation from this particular ith value of Y from the Y average or the naive mean of the data set. So if we square of it, it is the total variation. If we take what is due to the regression X, so that means from this value of X to the average, how much is the deviation square? We say B is the regression effect. And square of it, we take it, so it is B square. And whatever is remaining out of this, if A is total, B is due to regression, then C square is whatever additional variability which is not been explained, and this is the residual. Okay, if A is the total variability, B is due to regression, then C is what is being left or an additional variability, and it is the least square principle or the least square estimation. It gives the line beta that minimize this C square, this component. That is all individual values. We try to decrease this amount of variation, and this is called as least square variation. So if you see, it is A square is it is nothing, and then we have to sum it for all values starting from 1 to n. Suppose there are n values, so we will summation these type of deviations, square deviations, that is y to yi to minus y bar square, this is A, and the same way y cap from the regression line to the naive mean square deviation is B square, and the remaining C square is y cap minus yi, the square. So this is the overall regression picture. And the value or if we want to judge the accuracy of this model, it is being given by the R square value. All the linear models work on these principles. So how we can estimate the accuracy R square, that is sum of square regression divided by sum of square total. That means B square by A square in this case. So R square will be that amount. But there are certain assumptions in linear models. It assumes that the relation is in actual a linear one between X and Y. It is not a polynomial or a square. And Y, which is a outcome variable, is also normal for each value of X, normally distributed. That means it is not a skewed distribution. And for each value of X, Y is also normally distributed. And variance is also same for an outcome variable, for each value of an outcome variable, for each value of an X. That means homogeneity in variance. And the observations or the independent predictors, we say it is an independent predictors. So two predictors may not be correlated or does not have a covariance in between them. So we say they are independent of each other. X1, if it is multivariate, so if it is X1, X2, X3, all X1, X2, and X3 are not interdependent on each other. Okay. And the residual or the error is normally distributed having mean 0, but a unit variance. So these are the 5 assumptions or the fine prints we say for the linear regression. If we want to say how correlation and regression are related, this is of course for the two traits X and Y. So the correlation between X and Y is the regression times the standard deviation of independent predictor divided by standard deviation of the outcome variable or the outcome predictor. So if we want to test the significance and we want to test it at say n-2 degrees of freedom, so beta and the standard error of beta we need to know, because we hypothesize that if beta 1 is 0, the relationship is not linear, and if it is not 0, beta, that means slope. If slope is 0, there is no linear relationship. And if slope is not 0, that means other than 0, linear relationship does exist. So this is how we test the significance. And the formula for the standard error of beta, because we know here that in the denominator we need standard error of beta. And how to estimate that? We can say that it is the standard error of y on x, square of it, and sum of square of x and whole divided under root of it. So this is there. And when we say y cap is nothing but the simple linear regression here. That is the alpha cap plus beta cap xi, where alpha is the population mean and beta is the slope or the intercept plus slope, which is predicted. So using that, we calculate the standard error. And the important thing is when we generally don't check it when we do it by hand, we restrict our calculation up to R square estimation. But when you are using certain softwares, always go and check the boxes where it is said that the residual plot assay or do you want a residual plots? Because the residuals tells us how good our prediction is. Okay. If we want to particularly check for the assumptions, we say residual error is E for the ith trait is the original value y minus predicted value y for the ith observation or ith trait. Okay. So we want to check for all these assumptions. So you check whether in SPSS, stat tools or systat, anything, you check for the residuals. And let us see with an example. We want to check the predicted value, and y cap, the predicted value of say vitamin D in a sample is given by 20 an intercept plus 1.5 a slope, and the ith value of x, you can get the outcome yi. So if we take xi equal to 9.5, yi comes out to be 34. And if we want to plot this as a residual plot for prediction, so you can see that the y is 48 corresponding to the predicted value, which is 34. So what is the residual or the error remains is the 14 units. So this is how you check when the plot of residual is being made. That means these two on the left hand side are the non-linear. That means the linearity condition is not met. Whereas if such a plot comes, it is a linear. Both the residuals x versus y, these two plots are the linear ones. Okay. Then you can see for the homogeneity of variance. So we say if it is a constant variance is constant. So this will be the situation. And the second will be the constant variance situation. Just as on the lines of the linear relation, the variation is constant. That means the spread is not that much. But if the spread is irregular and very large, then you can say it is a non-constant variation. That means the scatter increases in a certain pattern, then we say it is non-constant variation. So if we say it is independent, that means it should come, residual should come in a straight line and no much variation. We say that x and y are independent, or the residuals are, this independence is measured because the error is also independent. And if the error is not independent, it will have to have some pattern or some relationship with the residuals. So if with these three things, let me go back, that to check the linearity, homogeneity of the variance, and the independence of the traits using the residual plots. So I leave this for you to predict how this residual plot is to you. According to me, if you can take a time and you can tell whether it is a linear, it is no. That means the condition of linearity is not met. The spread is having a pattern, no. So variance is huge. That means no common variance. Homogeneity of variance is also violated. And whether it is a linear, and then what was the third one? Yeah, independent. So it is not even independent. So if you get such a residual plot, that means your interpretation about the prediction model, or the model which you have taken, or the independent variables you have selected are not good for prediction, are not good for predictions. So by simply looking at a residual plot, if you go for a higher level publication, they will ask you to show the residual plots. So that is what, how important the residual becomes. Because indirectly we are saying that we are doing prediction, we are expecting an outcome based on certain trait. But how good is that? Whether we have left some other important traits. What about the residuals? What is this? Okay. And when we say that if there are more than one traits, we say it is multiple linear regression. It is not only the one trait. And what happens when there are more than two traits? That means the predictors are more in numbers. So we say that the effect of one predictor may be related with the effect of the other. That means the effect is confounded within the other variables. If x is confounded within y, then we need to separate it out. Here in this case, we have seen the effect of vitamin D, and then so we say that older men have lower vitamin D production. Okay, while older men have poor cognition power, also remembrance power. So what we say that it is affected, because this was the model I have taken an example from the net, and they have done this score, uh, subjective score, and in that it says that it could be these two confounding effect. So what we have to do, we have to adjust for the age in the model. That means the scores, the intercepts, the slope, and you have to adjust for the slope of the age. Slope into age interaction you have to take into account. So by putting in a similar plane of age, when age is held constant, we see the scores of the vitamin D and the slope. So it comes out this way in a plane. So we say on the plane, the slope of vitamin D is same at every age, Thus, the slope for vitamin D represents the effect of vitamin D when age is held constant. Another thing is, in case of multiple predictors, this will be the model that the expected value of an outcome y depends upon the intercept plus the slope of the first variable and the second slope and the third variable. X, Y, W, and Z are the different variables. So the each regression coefficient, beta 1, beta 2, beta 3, is the amount of change in the outcome variable that would have been expected for a per unit change in the predictor if all other variables in the models are held constant. That is why this beta 1 is called as a partial regression coefficient in case of multiple predictors, because it is the change in the y due to x when all other w and z other variables in the model are held constant. And this is how the multiple linear regression looks. So the functions of multivariate analysis is that it controls the confounders. Unless you are not controlling the effect of one other which of each other interactions, then multivariate analysis is incomplete. Then you test for interaction between the predictors. Okay, you modify them based on the interaction between the traits, and you improve the predictions. However, here I would like to mention, though I have not covered today, that the component analysis, we will do some math for that, but the principal component analysis take care of this multicollinearity problem. So we say a t-test is a linear regression. How? Suppose we divide the vitamin D sample into two groups, that is those who are having insufficient vitamin D based on certain criteria, and those which are having sufficient vitamin D. So sufficient vitamin D can be group having sufficient vitamin D in their blood can be called as a reference group. And we can evaluate these data with a t-test or even with a linear regression. So when you test for a t-test that whether the difference between the two groups is significant or not, so this is how the plot will come, and those who are unaware of this statistical point, they will delete these plots and say, oh, something might have gone wrong. But in actual, this is a plot for a t-test, and you see the results will come, and you have an intercept that represents the mean value of a sufficient group. Suppose this is an insufficient group, and this is how the scores of sufficient and insufficient group will help. So this is the mean of the sufficient group, the value of sufficient group itself, that is called intercept. And the slope represents, this is the slope of the line between sufficient to insufficient. This, oh, I have made it wrong. So this is the slope, and this difference between the mean, it represents the difference in the mean between the groups. And if the p-value is less than 0.001, that means it is significant. The intercept is significant, and it is very, very less, even less than 0.01. So we say that this slope is significant and it is negative. That means you see it is coming from top to bottom. From this group mean it is higher, and this group mean it is lower than this group. So it is negative. So negative 7.5 is the slope value. It is also an ANOVA, is also a linear regression, because we have an ANOVA table in linear regression. So what we will do here, we will divide into more than two groups, that is three groups. That is, one is deficient group, another one is insufficient group, and then the sufficient group. So we will take sufficient group here as a reference group, and we will see how the value of sufficient versus deficient and sufficient versus insufficient happens. So such a regression model is called as a dummy coding, where multiple binary variables, either present or absent, sufficient, insufficient, sufficient, deficient, deficient, insufficient. So they are either present or not. So we call it as a binary variables, and they are representing a category of happening or not happening. And such a variable is called as a categorical variable. So for categorical predictors, we are going to use the dummy coding. So the picture is with the insufficient, sufficient, and sufficient and deficient, and you will have the ANOVA table, and you can, you can estimate the intercept, and you can see how with the respect to sufficient group, the deficient group is negative 9.8, but it is significant here. And for insufficient group, it is also negative 6.8 is the slope with respect to sufficient one, and still it is also a p-value is high, is low. That means it is a significantly affecting between these groups. So there is a significant difference between sufficient versus deficient and sufficient versus insufficient group having the vitamin D level in their body. Other type of regression is the multiple linear regression, is a normally distributed outcome. The logistic regression, what is the main difference with the logistic regression is it can be done for binary outcomes and multiple categorical outcomes. The only difference is that in multiple linear regression, the outcome variable is continuous, whereas in logistic regression, the outcome is in the form of yes or no. That means binary, the mastitic animal, non-mastitic animal. So if you want to predict at how much level, what is the value in your herd, say the production level, after which there is a probability, likelihood that a non-mastitic animal will occur with the mastitis. So what you will do, you will take your data set and predict it using logistic regression. Another is the Cox proportional hazard regression. This is another form of regression where time to event is the outcome. Okay, so all the three, multiple linear regression, logistic, and Cox regression, they depend upon the predictor, or they depend upon the outcome. What is the outcome and what is the nature of that outcome? If that is a continuous, you use the multiple regression for prediction. If it is binary, you use it logistic regression, binary logistic regression. And if it is time to an event, time is the outcome, then you have to use the Cox proportional hazard. So if I say, by taking an example, so we say the outcome variable, when it is continuous, the example is blood pressure. Okay. And the appropriate multivariate regression model will be a linear regression. And example is that blood pressure in mercury, of mercury, plus a population mean plus B into salt consumption per day, that is teaspoon per day, plus the age of the incumbent and whether he smokes or not. So you see the predictor is either continuous or can be binary, right? Predictor is smoker versus non-smoker. This is an example of yes-no case, that is binary. So you can have both type of predictors, but the linear regression will be used since the variable is continuous. If the binary is the prediction, outcome is the binary, we have to use the logistic regression. And we say that the example is, in previous case, it was the blood pressure, estimation of the blood pressure in of Hg. Here we say, what is the odd that a person will have a high blood pressure? So whether he is having a high blood pressure or he is not having a high blood pressure. So that is the binary outcome. And we will take the same predictors like the salt consumption in teaspoons per day, whether he is a smoker or his age in years. The predictors are same. But what will become, will we have an outcome in terms of odds of having a higher blood pressure, right? How much the odd of an outcome increases. So the slope will tell what? That how much an odd of an outcome increases for every 1 unit increase in the predictor. Suppose you are increasing the salt consumption by 1 teaspoon. Suppose you are increasing the age in years, so by 1 year, and how much the chance is added on to have a higher blood pressure when a person is a smoker. And the Cox regression we apply when a time to an event is there. So we want to calculate the rate of death, or we want to predict how much will be the mortality in our herd in say coming year based on the previous year. This is an animal science example, but taking the same analogy, if we say what will be the rate of death, and we have used the same predictors, which is a combination of continuous as well as a binary predictors. So what a slope will tell, it will give a hazard ratio and tells you how much the rate of an outcome increases for every 1 unit increase in each predictor. That is how much percent or the rate of death is increasing in the changing the predictors by 1 unit each. So what are the pitfalls? What are the drawbacks of multivariate analysis? That means it takes into account the multicollinearity, especially in the biological traits. We say it is multicollinearity. All traits, all predictors are related with each other. So if suppose it is age at first calving, it is also related with the milk production, and calving interval, it is also dependent upon the age at first calving. So if calving interval and age at first calving are the two predictors for the milk yield, total lifetime milk yield, then we say that age at first calving and calving interval are related with each other. That means they share some proportion of variance. That means they are correlated. They are not independent. And this is the usual case with the multiple regression model, that multicollinearity comes into play and it leads to the confounding effect. And we then try to take care by decreasing the number of predictors or having a predictor which is a synthetic variable by using a dimensional reduction of data using principal component analysis. Then residual confounding, that means the residuals are not because the is high or low. If it is low, it is fine, but high residual may be due to this confounding effects because it has not been explained. And sometimes when we take more number of traits in a prediction, we tends to fit an overfitting model, create an overfitting model. So the interpretations are not right. The predictions go wrong or deviates from what we predict. So let us see these three things one by one. So multicollinearity arises when there are more than two variables and they measure the same thing. That means outcome depends and they are measuring the same thing. Example is if we use two predictors, that is weight of an individual and body mass index, both are included in a multiple regression model, then they will in fact cancel each other out and generally destroy your model. So model building, the outcome or the take-home message is the model building and diagnostics are a tricky business. You need to keep in mind what are the predictors you are choosing. So you have to choose the predictors so that there should be no collinearity, multicollinearity, and there should not be confounding also. That means you cannot completely wipe out this confounding by adjusting the variable unless a variable is having a zero effect, and which is not possible. That means all predictors will have at least non-zero uh, contribution in the outcome. So residual confounding will be there. Example is THI and season. So season is confounded in the effect of temperature humidity index because temperature and humidity depends upon the season. Then coming to an important concept of overfitting, let us see it in little detail, that in multivariate modeling, you can get highly significant but meaningless results. And this happens, you have the significant and you say, oh, it is very much significant, and you are excited, but these are meaningless. If you put too many predictors in a model, the model is fit perfectly to the quirks of your particular sample, but no predictive ability for a new sample. That is, when you are going to predict in the unknown sample or a new sample, then that model will not work well. But based on the priors, what you know, if you are using that in the same sample, it shows a high R square value and a great prediction, say 90, 91. But in practical, when you use to fit in other new sample, it doesn't work. So this is called as overfitting. And this happens because of you have considered multiple traits in the model. So suppose take an example and we say that you automatically to the software, you say that you automatically give us the regression model results. So it has given this type of result and it says you can see what were the variable variables were exercise, sleep, Obama, Clinton, and math love, and they say that you have to predict the optimism into that. So you see that the effect of the significant effect. So all these three, all of them are having a significant effect except the exercise. Okay, it is little higher than at 1% level. It is not significant, but all the effect of sleep, Obama, Clinton, and love for math. If you have these things, you will be an optimistic fellow. So does it make any sense to you? No. So in this case, we say that exercise, sleep, and high ratings for Clintons are negatively related to the optimism, and they are highly significant. And the high ratings of Obama and high love for math are positively related to the optimism, and they are highly significant. That means those who love math are highly positive. So let us see this situation, whether the model was overfitting due to number of variables we have chosen and we have included in the model. So let us see one by one. And if we see that, let us see optimism and Clinton. So here you see it is not significantly related. Clinton has no role with the optimism. If we see sleep, again, it is not having a significant effect with the optimism. Optimism has nothing to do with the sleep. If we want to see the exercise, again, it is nothing to related with the optimism. A person can exercise or may not exercise. Those who don't exercise can also be positive individuals. If we say Obama, it is significant at some level. The effect is that means Obama is a positive, optimistic person, and math love is highly significant, and it says that it is having a significant effect on the optimism. Those who are having a mathematical bent of mind, they will be optimistic. So this is the situation, and this is an example where they have seen that in order to avoid the overfitting, you need to have a larger sample size. And what will be the relation? They say that if you include a predictor, if it is two predictors and the sample size is 20, then you should at least have 30 sample size for the three predictors. That is, as a rule of thumb, you need at least 10 subjects for each additional predictor variable in a multivariate regression model. Otherwise, R square can come positive, high, but they may not be good for predicting in a new sample. So we say that statistical test, if we say that appropriate choice, we have seen in that example of blood pressure and salt and smoking and age. So that table tells you how much the appropriate and which appropriate statistical test you are going to use, and what depending upon the outcome variables and the predictor variables. So if we take that blood pressure, it is a continuous, and weight, continuous predictors, age, continuous predictor, whereas treatment is a binary predictor. So depending upon that blood pressure, which is a continuous outcome, so you would like to predict which type of regression you will use. Yes, you're right. It is multiple regression you will going to use. Okay. So now comes how to write a model. And I say writing a model has three parts. Part one is the equation itself. Many of the persons are getting afraid out of this. What is this mathematical jargon has come up, and they are not able to interpret. But after today's lecture, I think you can think that in a linear model, Yijkl is nothing but an outcome variable, and mu is the intercept, or it is the population mean of the samples, and A, B, C, and so many others are the effects we have taken in the model, and E is the residual or the error effect, which is contributing in the outcome Y. So mu is the overall mean. And what is this? That for the say Lth effect, Yijk, when we say, so what you have to do is you have to read from the kth effect on Lth effect on kth effect on jth effect on ith individual. Okay, of that you will have the Y value. This is nothing, just a way of notations. Part two is about these predictors. We have taken here 3 and so many others, but say ABC are the 3 predictors we have taken. So what is their effect? Whether they are fixed effect or they are random in nature. Fixed effect means that all the causal observations for that particular effect you have taken into the model. Whereas random effect means there is still something which you have not measured. It exists there. So based on that, you can classify the effects as fixed or random. It is little in detail. So we will not go into more detail of that. And we'll simply go to the third part, which is nothing but checking for the assumptions and limitation and making interpretation using the 2 parts. So taking the same example, and we say now that y the outcome is the weaning weight of beef calves, and we have taken the effects like A, B, X, and HY, S, and CM, and E is the residual which is left. So A is the age of the dam, B is the breed of the calf, X is the gender of the calf. See here, the gender will be a binomial, either male or female, and herd year season is a random effect, or no, is also a fixed effect. That means in which year, which season the calf was born, and in which herd it was born if there are multiple herds involved. And CM is the additive genetic effect, which is random in nature, and residual is also random. So we classify, this was the model. We have written a model that we will take into the effect these 4 effects: age, breed of the calf, age of the calf, sex of the calf, the herd year season effect, and the additive genetic effect, genetics, the pedigree of the calf, into the effect in predicting the weaning weight. So we can classify the part 2 is the explanation. That means you have a residual effects, fixed or random effects. So all effects were, say, fixed effects, except the additive genetic effect and residual effect, which are random in nature. So instead of stating that the variance of the calf additive genetic effect is 3000 kg square, one could say that the variance is 0.35 of the total variance. Okay. And herd year season effect. So this is the result we are interpreting. If that comes out to be 0.15, so we say it is the 15% of the total variation. Total variation in the weaning weight attained by the calf is being explained by the herd in which it is born. The management of herd means, by herd we means the year in which it is born, the effect of season of whether it was born in the winters or the summer or the autumn. So how much variation they are explaining into it. So if the value is 0.515, that is 15%, and the total variance which is left residual or unexplained is the 50% in this case, because only the effect of all the variance is 0.35 and 0.15 of the total variance in the herd year season. So we say 50% is explained, but 50% is remaining variation which cannot be explained using this model, and the weight can be expected or predicted. Weaning weight can in the calf can be predicted. And this also means that the means of the random effects are usually assumed to be 0. That means if we take the residual, its mean is 0 and unit variance. And calf should have been related, could have been related to each other because of common sire or common dam or mother. So that effect could be there. Now we say that the explanation, and we see whether the conditions have been met or not. So we assume here that there is no interaction between the age of the dam and the breed of the calf or the gender of the calf. This in this case particularly seems to be meeting, because age doesn't have effect on the breed or the gender. The second assumption is that the weaning weight have been properly adjusted for 200 days of age of the calf. So this we have to see that we have assumed that all the calf were measured at the age of 200 days. And we assume that there is no maternal effect. Maternal effect has no calf weaning weight effect on calf weaning, weights of the calf at the age of weaning, and age of the dam is known. That is also we have assumed. And all calves in the same herd year season were raised and managed in the same manner. So same management was given to them. So these were the limitations, or we have made an assumption. So as a researcher, we would like to discuss the interpretations, whether these assumptions were met or not. For example, if the interaction among the fixed effect exists, then using this model might give a biased estimate of age of dam, breed, and gender of calf, which might be biased the estimate of calf additive genetic effect. Maternal effect is very well known that it exists, and weaning weights depend on that. So we cannot take this assumption that there are no maternal effects on the weaning weight of the calf. So what we need to do is that, and from herd to herd, management also differs. So these effects will contribute. So we need to adjust in the effect, and we need to take their effect into account the reasons. So that is what it ends to one of the major topic of the linear regression or multiple linear regression. Now we will go for some discriminate analysis, or how to distinguish between based on a category variable, whether it will fall into group yes, responder, or no, non-responder, yes, mastitic or no mastitic type of case. And we will take as a concept, particularly with the angle of animal genetics in breeding. That means if we say that there is a genetic similarity, what does it mean? It means that they are alike based on certain traits. When we say it is dissimilarity, and if we are talking about genetics, so it is the difference. They are different based on certain traits. That means the genetics play a role in the similar genes, they are alike. If they are non-similar genes, they are dissimilar. So what we do, we have three things very closely resembling terms like discrimination, clustering, and dissection. So how we do discrimination? We do discrimination based on certain models or functions we develop, and into that we will discriminate into population A, into population B. Or we can have clustering, and based on certain rules, say if it is greater than this or less than this or is equal to this, it will fall into cluster yes, responder, non-responder, or in group A, group B, test or treatment or control. So these are called as classificatory problems. Both discrimination and clustering are classificatory problems. That means a new value comes and you have to decide where it will go to this group or that group. So you classify. And dissection, there is no clear-cut cases, and a lot of borderline cases exist. That means they can fall into either of the groups, in group 1 or group 2. Suppose we want to see the age and the purchasing power of an individual is a simple example of statistics, and we would like to see how it sees on the plot. And we say that there is a binary outcome, that whether he will purchase or not depending upon age. So this is how it will look. So who are the potential customer? So we assign 1 to this, who are likely to buy, and who are the potential customers who didn't purchase, we say 0 to them. So it is that. So 0.5 is the value here, where is the 50% is the probability of this. So what we will do, we will put a discriminate analysis, and we will try to do it through linear regression. So you see a simple line will be fitted, and it will be like this. And what you can do is you can draw another line, and you can say all those values which falls left of it, that means less by 0.5%, you have drawn a line. So, where this regression line goes 0.5, you draw a perpendicular to that. So these two values, if it is more than 0.5, then they are likely to buy. If it is not this, and as the age increases, it has that the potential customer below the age, at what is that age? It comes at 41 here. So below the age, it is likely that they will not buy. And before the age increases, the more number of customers are likely to buy compared to those who will not buy. So it has something, it gives something, but it is not the correct way, Even when you take it a fully discriminate into two population, those who buy and those who don't buy, and you say that it is 39 years of age, and that R square value is more than 81%, even then the 19% of the variation is left unexplained. 19%. 81% is only explained. So this is what I mean to say, and this variation is there in classification. So how the result of classificatory output will be seen? So you will have a matrix, that classification matrix, and it will tell you that when 0 was predicted as 0, there were 14 cases and 4 were left out. So it was correct up to the level of 77%. When 1 was predicted 1, there was only 16 cases and 5 cases were left out. So it was 76% correctly estimated. So what is this 5 and 4? So 5 in first case are false positive, which are likely to get by. They will come into those category that they will buy, but they will not buy. So they are false positive. And those who are likely to be buy, and they were classified into false negative 5 in this case. So this is how you will interpret, and it was 77 for the first case and 76.2 for the second case. So when we say what was the average or the overall accuracy, it was correctly classification was done at the 76.9%. This is how you have to interpret the results. And I told you it is not correct because we need to use the function for binary variables. I have already told that logistic regression is required, and it fits the sigmoid curve. And we use this curve, and the value of point at 5, it is defined, whereas it is not defined, this function is not defined at the value 1 and value 0. So how this function is being explained? It is explained for an x variable, that Euler raised to the power the, if you say this what is raised to the power in both the case, it is nothing but the multiple linear regression model where there are p number of traits. So this is same. Okay. Only thing is that Euler divided raised to the power the prediction. That means you can say it is nothing but the y cap. So e raised to the power y cap Euler 1 plus Euler. So this will tell you the odds of likelihood that whether it will buy or not buy this function. So how to interpret? So depending age as a coefficient, regression coefficient, we have seen that age is highly significant, and age has a role to play because the coefficient of age falls within the standard value and world value, and you can say that age is a significant determinant in the purchasing power. And when you see classificatory metrics, you see the percentage of classification has improved compared to that, whereas the overall accuracy remains the same. So how you will do it? If you do want to do it under SAS, you have to go under the analysis tool and select the regression and classification. And under classification, you can use discriminant analysis. So you will have under that option both discriminate analysis and logistic regression. So you have to use how to do it. And there is a slight difference that you for discriminate analysis, you can use the dependent variable with more than 2 possible outcomes. And you can have logistic regression, and it has some assumptions that it is more an assumption dependent, and normality and constant variance should be there. And it is logistic regression is good when you want to have some borderline cases in your data. So another is a genetic divergence analysis, and then the third variation, multivariant analysis. So it was done and it was used to calculate the potential candidate sires, young sires, sons of progeny of young sires, and you want to include them in a progeny testing program. So there you have to use that you need that they should not have the same genetics. So you classify into two. If you want to take two bull to be potential sire under a testing program, progeny testing program, so you classify them into, you have number of bulls, you classify into 2 groups or 3 groups, and from each group you take one sire for testing, because progeny testing is a time consuming, labor intensive and costly affair. So we first do for the divergence analysis, and genetic distance, we call it a D square. Who gave this concept? It was Prasant Chandra Mahalanobis, who gave in 1930. And it was a very important measure which was used in the Second World War, when they used on this. He was an Indian statistician from Bengal, and using the dead bodies in the Allied forces, or they were not able to tell which nation the person belongs because they have died. Their mutilated bodies were there. So using the craniometric, the skull measurements, he divided into different groups, and then they were different. The bodies were differentiated and dispatched to their respective countries. So, and since then the history has changed. This Mahalanobis distance is the multivariate statistics which we use, and this is very much similar to those of the Euclidean distances between the classificatory problems, which is the most common one. But Mahalanobis distance has certain advantages. So you see here, it is just a pictorial representation of the data set, that there are two groups, one is blue and other one is red. So this is how an overlap is there of blue and red, and you want to discriminate this overlap. So let us see, and you can say that these data points were of the body measurements, and you can say height at the withers, body length, chest girth, pouch girth, or leg length of an individual. You have for say n number of animals these data from two groups, first group and second group. And then what you will do, you will measure a distance, that is each point you will measure it from the mean of that group mean. Okay, and this type of distance is called as Euclidean distance. How to estimate a Euclidean distance? It is the square root of the square of the deviations. So each individual point, you have to take a mean. Suppose this is the mean, and you want to calculate this distance of this particular point. You take the difference of this point xi with the x bar population mean, square it so that you get off the negative thing, negative values, because something will be above positive 0 and something will be below 0. These all are negative values here below. So you square it, and then you simply add on to all the values, summation of all the data points in the set of series, and then you take the square root of it. So it is the simplest measure, most common used measure. So how you do it? You have some means, and you then see how their variance is shared or not. If there is no shared variance, that means no covariance. That means x and y are not correlated. And if it is positively correlated, this is the plot you will have. So you say it is a variance covariance matrix of all the observations. So this is how it is shown, the variance covariance matrix, where the diagonal in the matrix is nothing but the variance, whereas covariance is the off diagonal on the matrix. So those who are familiar with the concept, just to tell them how the correlation is seen and how a different multiple, when the data points are very large, when thousands or lakhs of animals are measured, and say 50 or 2000 variables are there. So this is how you will not be able to solve using the linear algebra, but you have to go for the matrix algebra, and this is how the matrix is seen. So you will calculate the distance based on the variance covariance matrix. And here comes the concept of the vectors. And suppose we want to say that x is x1 and x2, and this is the 0 of x1 and this is the 0 of x2. So if we say that for x1 value is 2 and for x2 the value is 1, so this will be the vector from the origin 0, 0, 0 coordinates to this. This will be the vector. So this is how we design a vector, and their vectors have certain properties if you want to see in the matrix form. So here E is an eigenvector or a special characteristic vector, where you can see that if it is multiplied by a certain matrix, then is equal to the identity matrix, and the same vector is E1 by E2. So if we imply and we derive, nothing much to bother and worry about, but you see that if this is the vector E1 and E2, 3 and 2, so only thing what I mean to say is that each characteristic vector or eigenvector is having certain scalar quantity, which is this 4. This is called as the eigenvalue. How does it comes? That if you multiply the matrix with same eigenvector with the same matrix here, then it will come out, same matrix will remain, and same eigenvector will have some value or a scalar value, which is called as the eigenvalue. So what a vector depends upon the magnitude of the values, So vector will go on. It can be as long as that it can go so out of the space, and it may still not end because it depends upon the magnitude. So what we do generally, we scale down the eigenvectors to the length of unit 1. And how you do it? We do it by using a Euclidean distance and dividing each vector by its Euclidean distance, and we call such a vector as a scaled eigenvector. So scaled eigenvectors doesn't have a eigenvalues, so that thing doesn't matter. But the two scaled eigenvector will have a different value. Suppose based on the matrix, now you got that some value of this vector, and it has a 0.8 for x1 and 0.5 for x2. So this is the vector it is representing. And how does this vector come? So it is exactly on the line of the linear regression line. So it fits the line of an eigenvector in the direction of the maximum variation in the data set. So major axis regression, we call this. So that is the regression. So suppose if we draw a axis here, straight line here, though it is not straight. So if we draw a straight line here, so it will not explain, the majority of the dots are not in the data set. Whereas in the regression line or the major axis regression set by the eigenvector is in the maximum line of the regression. This is the example that 4 is an eigenvalue and it is determined by the lambda, and each eigenvector is having an eigenvalue. So now based on the two eigenvalues, and there is a property that the second eigenvalue is perpendicular to the first, and third eigenvalue will also be perpendicular to the second and the first. So each eigenvalue is perpendicular to the other eigenvalues. And if there are two eigenvalues for two traits, then there will be so these first one, red one, is the lambda one, having a scalar value 11.77. That means it is having in the line where the maximum variation or the maximum dots are near to this line, red one. And the blue line is the second line or the second vector along which the maximum, the distance of all the data points is there. So the spread is along the second. So how much is the total? Total is somewhere 11.77 plus 1.55. And this is the total, and 1.55 is the eigenvalue is the much less than the 11. And similarly, if we draw a third eigenvalue or third vector in the direction where the variation is there, it will be still less than the second eigenvalue. So you have estimated the eigenvectors, and based on the eigenvalues, then you will calculate or the distance of each value based on this. So you remember the actual value was this. Actual was this plot, okay, x1 and x2 traits, but somehow you have made this plot based in the eigenvectors, first and second. Now you calculate the distance of each data points. Earlier we were collecting based on x1 and x2. Now based on this new eigenvalues which you have created a vector, you calculate the distance of these vectors and then rotate it. So now you see, now you forget about this original. Now you think this is as a new scaled vectors, and you can calculate the distance based on this first eigenvector and second eigenvector. So the Mahalanobis distance is calculated using these. In case of matrix notation, it is nothing but the deviations. So deviation matrices and the transpose. Suppose x1, x2 and minus of x bar, xn bar. Then you transpose it, that rows becomes column and column becomes rows. So it is this column, this row becomes column, and this row becomes this column. So this is this portion. You transpose it and you have a variance covariance matrix, which I've shown you earlier. Diagonal is variance and off diagonal is covariance. Then you transpose it and you multiply it with the deviation. So what you will get is the d square. And based on this d square, you can classify a new subject, whether it will go to the responder group or non-responder group. Okay, same. So you have some prediction, you will have take some traits, and based on that you have something, you have the mean of this group, you have the mean of this group, and then you will add this value to which one is the smaller is the distance. It will go to the d square. The smaller is the d square. That means it is this point is, if this is smaller, then this point belongs to this group. And if this distance is smaller, this point, new object, belongs to this group. So this is how you calculate the linear distance. But the advantage of Mahalanobis distance is that it takes into account the scale and the size. So whereas Euclidean distance is not. Suppose the income is in thousands and lot size is in 1,000 square feet. So the measure in this A group will be determined by the income. In this group, it will be taken away by the income itself. And in this group, it will be taken away by the lot size. So in ABC, you have different effects being taken away by the depending upon the scale of the income or the lot size, if it is square feet or 1,000 square feet or thousands. Or so Euclidean distance have some issues. Whereas if you standardize this data, then you may have equal thing. But Mahalanobis distance does that. And I have shown you this in the same example, that d square distance is the Mahalanobis distance. And here X is the matrix of data matrix of all the vectors. And M is the mean value matrix of all independent variables. C is the inverse of covariance matrix of independent variables. And T is the vector which is used to transpose. So this is how the Mahalanobis distance. And in genetics, if you want to put it, so we will say that J and K are the two genotypes, and I to P are the number of traits. So for each traits, you will define different genotypes, and you calculate the D square. Those who are in the same group, you can say that they belongs to the same genetics. And this is how we do it for every newcomer or the new population based on certain model, discriminate model you have developed. So every new member which will come, we will calculate the D square. If it is smaller, we will put into that group, and we calculate the centroid again. And then when the new entry 2 comes, we calculate the distance again. And based on the minimum distance, we again classify into that group. And this will go on. So this is a flow diagram showing that how to start. You divide the input number of clusters. And this again has a lot of science behind that, how to determine how many cluster initially you will take. So you do say based on if it is a supervised learning, so you can, based on your practical observation, if you have two groups, you tell them that you divide into two clusters. Or in the sires, if we say in the genetics, if you know that the progeny is from these 5 sires, you ask him to have 5 number of clusters initially, and then calculate their centroid or the center value, and then calculate the distance of every newcomer, new animal, and based on the minimum distance, you keep on classifying them. So friends, thank you for patient hearing. I think I have covered major topics of the multivariate, except the component reduction, which is also a separate part, and it requires a lot more time. So thank you for patient hearing, and I hand over the proceedings to the organizers, please.
Thank you, sir. Thank you very much.
Yeah.
Participants, if you are having any queries, please write down in the chat box. And Dr. Vohra sir is with us. A very specific queries regarding this multivariate analysis, please. So as
yeah, I can see, Sajid, that somebody has written that canonical coefficient or coefficient only. It is, if the canonical variant analysis, we call it canonical coefficient. Otherwise, in a linear regression, it is a coefficient only.
Another person is asking, sir, in many research paper, I observed that they use PCA and cluster analysis both. Is it necessary?
Yeah, it is just a way of substantiating your work or your results. If you have done it with the PCA, you use it PCA. And if you want to do it both, you do it both. But what I would say, the major difference as a statistician, you should know that principal component analysis we usually apply to see the substructuring within a single population. And how to know that? you should know based on your experiment whether it is from the single population. And cluster analysis is when you are having more than one group or one population, and you want to see whether these two groups are actually belonging to the two group, or the new entrant is belonging to the two groups. So you will say a classification that with this much of accuracy we can classify. And if you want to say no, it seems to be a single population, but based on these traits only, we want to say that whether a subgroup is available within a single population or a structuring is available within a population. So you go for a component analysis, and based on the eigenvalues and eigenvectors, you can determine the component, first component and second component. And usually this first two components can explain the maximum variability. Based on that, you can see if the dots or the data points are clustering, and you can say that they are into two separate clusters. So you can say that this population, though appear to be a single population, but may have a substructure or subpopulation present into them based on the traits, whatever you have taken. Whereas in discriminate analysis, you say that it is already, you know, that I told you that it is a supervised learning. You say classificatory problems are supervised learning, whereas a principal component is a non-supervised learning. Okay, can we apply linear discriminate analysis while comparing? Yes, of course, why not? This you should apply. And does it require to include independent variables and dependent variables in PCA, particularly in social science studies? So I cannot comment particularly in social science studies, but you want to see PCA itself is a synthetic variable. So you can use anything, independent predictors as an independent predictor, and all sum of them will be taken out. And it takes into care the multicollinearity. So the correlation or the covariance between the independent predictor is taken care of. So it leads to less confounding and more accurate effects. In social science, if I am make to guess, so I say yes, you can take. I think
Okay,
we
thank
all
you.
learn from social science. We are genetics and breeding, or in animal science, we have to learn from the social science only. That is the only option.
Okay, sir. Thank you very much, sir.
Okay, thank you.
For such a
Thank you
nice
for asking
and
questions.
knowledgeable presentation.